Welcome back to the lesson of Chapter 4, Arrangement of Electrons in Atoms. As you can see, we are going to have a main idea of this lesson. Light has characteristics of both particles and wave. I would like to underscore on these words, on these words regarding wave. You might ask about waves. After we define what wave mean, we are going to see the relationship between particle and wave. So let's First characterize wave. Characterize first wave. Let's characterize wave. Characterize wave. How can we characterize wave? Wave has wavelengths, and the other characterization of a wave is by its frequency, and the other one is speed of light, speed of light. Before we fully characterize a wave, let's see one example that indicates how wave behaves by using one samples. Let's have a wave. As you can see, wave can be described by its wavelengths and frequency, but let's see first how wave behaves. Let's have this figure. As you can see, wave have a starting or resting ground. We call this resting ground or resting position. This is resting ground. Resting ground. And there is also a maximum height of a wave. We call it amplitude. Maximum height of the wave, and also the distance between successive waves. We call it wavelengths and noted by lambda. So when we define one cycle of a wave, it's simply the consecutive crust. The observation of consecutive crust will give us one cycle. So this definition of one cycle will help us to later describe what frequency means. For now, let's keep on defining some of the characteristics of like wavelengths, frequency. So as you can see from the picture, we know about amplitude. We know about the distance between successive crusts. So this we have already defined the distance between two crusts. We call it wavelengths, And the maximum height a wave can acquire, we call it amplitude. And the next definition will be, how can we relate wavelengths with frequency. How can we relate? So there is one relation that relates wavelengths and frequency is C is equal to lambda times frequency. The frequency is denoted by V. So the product of lambda and frequency gives us the speed of light. As you know, the speed of light, this is the speed of light, which is constant if it is traveling through space, a little lower when it is traveling in the air. But we adapt the speed of light as the speed with which it can travel through vacuum, which is 3 times 10 to the power of 8 meters per second. This speed of light is equated 3.0 times 10 to the power of 8 meter per second. From this, what do you understand? You have lambda, the wavelengths, you have the frequency, so the product of lambda times frequency is a constant value. So by rearranging, we can have so now we have C is equal to lambda times frequency. We have already 3.0 times 10 to the power of 8 meter per second, which is C, is equal to lambda times frequency. So as you can see, the product of lambda times frequency is the constant value. So let's rearrange it to see the effect of C is equal to lambda times frequency. Solve for lambda. Lambda is equal to C over V. As you can see, lambda and frequency are inversely related. Lambda and frequency are inversely related. They are inversely related. What does it mean, inversely related? As the wavelengths increase, the frequency decrease, or vice versa. As frequency increase, the wavelengths decrease. Let's see this by a picture so that we can easily understand the relation between lambda and frequency. We have this thing. We will take two scenarios, and the other scenario will be this one. Let's take two samples for comparison and see how the waves are different. If you can see the two waves, they are somewhat different in amplitude. They are somewhat different in amplitude. Look the amplitude and look the amplitude. A wave can vary in its amplitude. A wave can vary in its and its wavelengths. Look, now we are interested here the distance between successive crests or successive height, and see again the distance between successive height. In both cases it's wavelengths, but as you can see, the distance between successive waves, we call it wavelengths. One is short and the other is long. So which one do you think has high frequency? Let's take this is example A, and this is example B. So which one has high frequency? High frequency. It's no wonder you just go back to the mathematical equation which says lambda is equal to the speed of light over frequency. If we separately see the relationship between lambda and frequency, we have this relation. Since lambda is inversely related with frequency, inverse relation, which means when one is up, the other must be down in order to indicate frequency. So as you can see from the picture, the more wavelengths you have, the less frequency it will be. The higher wavelengths, the less frequency it will be. And next, again, lambda is related inversely with frequency. As the wavelengths decreases, look, the distance between the wavelengths decreases, the frequency increases. So in the case of B, this is high frequency. High frequency. This is low frequency. Low frequency. By now you can easily compare wavelengths and frequency. So now we're going to define what frequency means. Frequency is simply number of waves in the given time. The highest frequency. So frequency, let's define frequency. Frequency is equal to number of waves passing in the given space at the specified time given. Let's say in 1 second you might have 2, 3, 4 waves can pass, and in the case of the highest frequency, and in the low frequency you might have only 1 wave passing at a time. So by now the picture will clearly indicate the relationship between lambda and frequency. So these are the two main characteristics of a wave. Wave has wavelengths, and wave has frequency. So this is in general the property of so to sum up the characteristics of wave, we have said that wave has wavelengths, wave can be described frequency, wave can have frequency and wavelengths related inversely, and we have seen also this thing. And a wave can have a maximum height, amplitude, the wavelengths can vary. So these are some of the qualities that differentiate one wave from the other wave. So to sum up, we are going to see if it is wave according to the main idea. Wave, particle have wave, and we are discussing about light, but we are heading to discuss about electrons. So the electron, next time, next class, electron, this is light, is a wave. Is a wave. How about is a wave? How about electron? How about electrons? I want you to think over on this. How about electrons? Are electrons behave like a wave? We're going to discuss on this next lesson. So